Hey folks, welcome to this channel and welcome to this video. I am Saptarshi Mukherjee. I am a software engineer 3 at Google and a computer programmer. So in this video, I am back for a discussion of the fifth problem of CSES problem set of dynamic programming, that is removing digits. So let's take a look at the problem. The problem says that you are given an integer n, and at each step you may subtract one of the digits from the number. That is, whatever number you have, you can take any of the digits and you can subtract. Then how many steps are required to make the number equal to 0? So simple question, you are given an n and you have to reach that to 0. What can you do at every step? Subtract one of the digits. In that way it will definitely keep becoming lesser. At one point you will reach 0. You have to print what is the minimum number of steps, and you have to solve it for n going up to 10 to the power 6. So you cannot have a big O n square n cube kind of algorithm. It has to be big O n log n, something like that maximum. So let us take, so basically this is a kind of problem where you have to reach from n to 0 in whatever number of steps. Now we have 27 over here, the output is 5, so let us explore 27. For 27 we could have gone either with 2 or with 7. We could have said, hey, subtract 2 or subtract 7. If we subtract 2 we would have got 25, otherwise we would have got 20. For 20 we would subtract 2 and get 18. For 18 we can subtract 8 or 1. Let's see, I think they have subtracted 8. Yeah, they have reached 10. So we will subtract 8, reach 10. And from here we will come to 9, and from there we will come to 0. So in 5 steps it's completed. However, if I go from 27 to 25 in this way using 2, from here also if I apply, or maybe some other things like 5, I get 20. And from here more or less the same kind of a journey. I get 18, and from 18 it's 8 to give me 10. From here it's 9. From here it gives me 0. So you can see along one way, this is one way, it gives me 6 steps. The other way gives me 5 steps. Now what we want to know is that, hey, which path will give us the smallest number of steps? Now what is common over here? At some point of time we are going down from 27 to something like 20, and we are asking the same question, hey, you can be reduced down to 0 in how many steps? I will take 2 more steps compared to you, or maybe 1 more step compared to you. We are asking that question, hey, 20 will take how many steps? 25 will take how many steps? 25 says that it will take total 5 steps, and 20 says that it will take a total of 4 steps. And from there somehow we can say that if we follow the above path, we will get 5 plus 1, 6 steps. This will give us basically 5 plus 1 equal to 6, while the bottom way will basically give us 4 plus 1 equal to 5. Which means if I take the minimum, the 5 is the minimum I get. So what am I basically doing? I'm saying from 27, the immediate steps are only finite possibilities are there. In this case, 2 possibilities. If it would have been a 3-digit number, we would have 3 possibilities. But we have only those few states where we can go. From there, again, we have to optimize. So look at them as different states. And this is where I would remind you, I would bring to your recollection about a previous problem that we solved, minimizing the coins to get something. We can take a look at the problem. The problem was basically minimizing coins, where we said in order to reach a certain sum, what is the minimum number of coins that we need. So there we basically said, hey, if you use the coin 1, remaining part is 10. If you use the coin 5, remaining part is 6. If you use the coin 7, remaining part is 4. For those 10, 6, 4, find out what are the number of coins needed, x, y, z. And based on that, find out the answer. So we basically reduced this main problem of minimum number of coins to get 11 to minimum number of coins to get the smaller states. So somehow the answer could be directly obtained from the answer of the smaller states. So now if you look at this, here also it's the same thing. So whenever you have to reach from one place to another place, in that minimizing concept, so it was the same thing. You started the process, you said till it reaches the base case which is 0, I will keep on continuing the process. So it's similar in some ways. And here you basically have to subtract something at each step. The end result is 0. So more or less the same things. You start at some end, you end at some 0, and you have some choices in between. How do you decide it now? You delegate the task. If you are going in a top down way, in a top down way, you will delegate the task. So you can basically define your answer in the form of a DP state, DPN. DPI basically will tell us that the answer for I, number of steps, minimum number of steps to reduce I to 0. The steps basically refer to the kind of steps we have seen, subtracting one of the digits. So in this way, we can say that if I has some digits d1, d2, d3, then basically your DPI will look something like this. DPI is equal to the minimum of 1 plus dp x, where x is a digit of I. So for every digit of I, if we know the dp of that digit, the dp of that digit subtracted from the number, so it will be something like I minus x. If we find the minimum value out of all those DP states, this is an easy expression. This is known as a recurrence relation, which tells you the relationship between your DP states and other DP states. And if there are some exceptions, like base cases, you should write them separately. In this case, probably the base case would be 0, in which case you should write there are 0 steps needed for 0. So that's how. So these are your sub-problems. From your DPI, you can actually call these sub-problems and solve your problem. Or you can approach it in the bottom-up way. So in your top-down way, you can basically apply a recursive kind of an implementation, where from DPI you will call the DPI minus x1. You will call this function to get you will call a function recursively to get this value. You will call something else, and you will do this with memoization, recursive with memoization. You can refer to that video, the previous video where we discussed these basics of recursion, memoization, and then tabulation. And we discussed the differences between memoization and tabulation. So we actually saw that unless many of the states are skipped, in this case some states will be skipped, but still, since you are subtracting a digit at a time, which is less than 10, so most of the states you will be visiting. So it's better, if you are sort of considering all the steps, it's better to go for tabulation. If you're covering all the states in either case, then it's better to go for tabulation, which will have other advantages for you, like recursion, stack space, etc. are not involved. So when the call happens in this way, from the biggest to the smallest ones, this is known as top-down approach. You have a bottom-up approach where you'll basically say that, let's say n is equal to 6, or basically you will have a table. You can have 27 also. So basically you have, for 20 it will already be filled with 4. Basically you will fill everything from left to right. We fill everything from left to right. Whenever we are filling something like 25, let's say, we will say, okay, 25 minus 5. So we will read this and we'll update this that okay, this is 4 plus 1, 5. So we will go over here because 25 minus 5 is equal to 20, and we will go back to 23 as well by subtracting 2. At 23 also, I think the similar 5 should be there, so we will choose a smaller one. So that is it. So basically looking at the sub problems which are already solved and solving the current problem, if you're moving from left to right in that way, that is known as the tabular approach, tabulation, or this is the bottom up. So let us look at my implementation there. Yeah, I basically traveled from 1 to n, and I started num at I at any number, and then I'm going downwards. I'm basically saying while num is greater than 0, keep on doing this. So extract a digit and consider all the digits. So in this while loop I'm considering all the digits. If a digit is 0, I'm not considering it because it will leave it to the same place. Now I am iterating from I equal to 1 to n, means it is a tabular thing. I'm going from the smallest subproblem to the largest problem, or smallest subproblem to the largest subproblem. That is why this is a bottom-up method, from the smallest to the largest. So when I'm saying, hey, take this 1 plus answer of I minus d, it is already solved over there. Memorization is the opposite thing. We ask the smaller problems to be solved. If it is already solved, we get the answer. Otherwise, they solve it and then give us the answer. So that's it. Here the smaller problems are solved, then we fetch their answers to solve. In case of memorization, we delegate. We start from the largest problem, then we delegate things to smaller problems. So what's the time complexity? You can see it's big O n, and how many times will this loop run? You can say there are 6 digits maximum in each number that you are getting. Starting from n going downwards, you'll have maximum 6 digits in a number. So this loop will run maximum 6 times. So the total time complexity or number of steps comes out to be 10 to the power 6 multiplied by 6. So 6 into 10 to the power 6 is well within our time limit. So that is this problem, removing digits. I'd also add that this is similar, like this particular paradigm of reaching from n to 0 or somewhere to somewhere is very similar to the very popular shortest path problem, where we say, hey, you have to reach from A to B, and these are the intermediate nodes. So over there also, in case of shortest path problems, we have a similar strategy. We say this is A, this is the destination D, let's say, and then there are some, or let me name this as source S. Then you have some extra things like A, B, C, X, Y, and so on. What we say is that from here, if you can reach here and here, there is some algorithm which says, there is some algorithm which works for positive edge weights. There are some terms like that, which basically works on the principle, hey, find out the minimum for this, find out the minimum for this, and then you are halfway done. Or basically proceed from the leftmost side and see that which one you're able to reach in the smallest possible time, carry that forward. There are a lot of those approaches. Greedy DP combined. So yes, in some of those approaches, we do use the DP approach. So that's it. I hope you got the crux of the problem. I hope you'll be able to solve the problem yourself. See you all in my later videos. Goodbye.